Find ID, or the drain current, using LCM equations of this NMOS amplifier, so we don't have to account for any short channel non-idealities. Given VTNO, which is the threshold voltage, which equals 0.4 volts, Kn, which is this product or transconductance parameter, not to be confused with GM, which equals 1 milliamp per volt squared, gamma, which is the bulk threshold, equals 0.2 volts to the 1/2, lambda equals 0.1 volt to the -1, also known as the MOSFET device parameter for IV characteristics, oxide capacitance Cox, which is 1.004 microfarad per centimeter squared, 2 phi f, or surface potential equals 0.88 volts, width equals 1 micrometer, and length equals 0.1 micrometers. Starting off, we should label the 3, or technically 4, parts of this NMOS transistor. Here we have the gate. Above we have the drain. Below we have the source. And since it's not explicitly stated, we can assume that the body, also known as the substrate, is automatically equal to ground, or otherwise the lowest potential of the system, which is ground. To analyze this MOSFET, we have to first see whether or not it is on or off. We can tell given VGS being greater or less than the threshold voltage VTN. So starting off, we need to see that VG of VGS is this voltage at this node of the gate here, connected to 2 volts. We can call that 2 volts. And VS, which is this node down here, is automatically connected to ground, so we can call that 0 volts. Intuitively, VGS equals VG minus VS, which equals 2 volts, because 2 volts minus 0 volts equals 2 volts. And we need to compare this to VTN, which is not the same thing as VTNO, because this does not account for body effect. To see if body effect does exist, we need to see if there is a potential difference across VSB. But as you can tell, they're both at ground, since VB equals 0 volts, as well as VS. So we can confidently assume that since VSB equals 0 volts, I'll put it up here, no body effect. Now, moving on, going back to the VGS, it is greater than VTN, which we now can assume is VTNO, which is 0.4 volts. So the device is on. This brings us to our next step of the process, where we need to see what mode it is in. It's either in triode mode, some call it linear, or saturation mode. To determine which mode it is, we need to find the parameter VDS sat, or the potential from the drain to the source, and saturation to determine whether or not it's in that state. To find this, given the long channel model equations, we know it is equal to VGS minus VTN, which is again assumed to be VTNO since there's no body effect. This equals 2 volts minus 0.4 volts, which we found before, and that is 1.6 volts. Now we need to see what VDS is in comparison with VDS sat. We can see that VD is 1 volt as it is connected to this node here, and VS is again 0 volts. So VDS equals 1 volt. Now compare this to VDS sat. It is, of course, less than VDS sat. And as you know, if it is less than VDS sat, then it is automatically in triode mode. This gives us all the information we need to calculate the current going through ID, which is over here. Knowing that it is in triode mode, I'll call it tri here, it is equal to the following. Kn times VGS minus VTN times VDS minus VDS squared over 2. And that's all we need. Kn, as given from the top parameter, is 1 milliamp per volt squared. However, we need to standardize that to amp per volt squared. So we can call that 1 times 10 to the negative 3 amps per volt squared times VGS, which was 2 volts, minus VTN, which was 0.4 volts, times VDS, which we found to be 1 volt, minus 1 volt squared, which is just 1 volt squared over 2. And putting that in the calculator, we get our final answer of ID equal to 0.0011 amps, which is equivalent to 1.1 milliamp. If you have any questions, please leave in the comments below, and good luck.